energy levels for electron in a hydrogen atom are evenly spaced, farther apart near the nucleus, closer together near the nucleus, or arranged randomly. This is how the energy levels in a hydrogen atom would be spaced. The difference between the first and the second energy level is the greatest, then the difference between the second and the third, and the difference between the energy levels decreases as you go away from the nucleus. And finally, when all the energy levels converge together, you reach the convergence limit. That's when you say the electron has reached n equals infinity, beyond which the electron will be out of the atom. So the answer to this will be they are farther apart near the nucleus and they go closer when they go away from the nucleus. Which statement is correct for the emission spectrum of hydrogen atom? The line converge at low energies. We've already seen from the previous question that the lines converge at high energies because they are farther apart from the lower energies, and then the lines go closer till they all merge and converge at the highest energy, or n equals infinity. So this choice is wrong. Lines are produced when electrons move from low to high energies. When an electron needs to move from a lower energy to a high energy, it needs to absorb energy which is equal to the difference between the two energies. Whereas when an electron needs to come down from a higher to a lower energy, it needs to release or give away the energy which is equal to the difference between the energy of those two levels. The question here is asking about the emission spectrum. In an emission spectrum, the energy is released when electrons come from higher to lower energy levels, and a line is produced corresponding to the frequency of light that's emitted. So lines are produced when electrons move from lower to higher energy levels for an emission spectrum is not true. To understand choices C and D, we need to know a little more about the electromagnetic spectrum. So the electromagnetic spectrum that we receive from the sun ranges from very high energy gamma rays all the way to low energy radio waves. So the order is gamma rays is highest in energy, followed by X-rays, then ultraviolet, then the visible region due to which we can see, and infrared and radio waves. For the IB exam, you're also required to know the qualitative relationship between color, wavelength, frequency, and energy across the electromagnetic spectrum. Wavelength, symbolized by lambda, is the horizontal distance traveled by the wave in one cycle. It's also equal to the distance between two humps or crusts, which is also the same as the distance between two consecutive crusts or dips. All electromagnetic radiation travel with the same speed, c, which is 3 times 10 raised to 8 meter per second. In 1 second, it travels 3 times 10 raised to 8 meters. Frequency, represented by f or nu, is the number of cycles the wave makes in 1 second. The unit's number of cycles per second is also called hertz. Now, though in actual fact, a light wave would travel 3 times 10 raised to 8 meters in 1 second, here, for convenience sake, let's suppose this is the distance traveled by the wave in 1 second. So let's find the frequency or the number of cycles this wave makes in this 1 second. The first wave makes 1, 2, 3, 4, 5 cycles. And the second wave makes 1, 2, 3, 4, 5, 6, 7, 8 cycles. So when the wavelength is high, the wave can only make a few cycles in 1 second, whereas when the wavelength is low, a lot more cycles needs to be made so the wave can travel the same distance in 1 second. Hence, high wavelength means low frequency, and low wavelength corresponds to high frequency. The relationship between speed, frequency, and wavelength is speed is the wavelength times frequency. Since frequency is the number of cycles made by the wave in 1 second, and the horizontal distance of one cycle is one wavelength, the total distance traveled by the wave in 1 second will be the frequency times the wavelength. Since speed is the product of wavelength and frequency, longer wavelength means less frequency and shorter wavelength means higher frequency. The energy of a photon of light is proportional to its frequency, equation being energy equals Planck's constant times frequency. Hence, higher energy means higher frequency and shorter wavelength. And lower energy means lower frequency and longer wavelength. And now back to our electromagnetic spectrum. We see here that higher energy radiation have shorter wavelengths, so the cycles needs to be more frequent, or they should have higher frequency to cover the same distance. And the low energy radiations will have longer wavelengths, so the cycles need only to be less frequent, so the lower frequency to cover the same distance. The violet end of the visible spectrum is the region closer to the ultraviolet region, and the red region of the visible spectrum is the region closer to the infrared region. So the order of decreasing energy levels between ultraviolet, visible, and infrared is ultraviolet is the higher energy, followed by visible, and then infrared. The reason why I highlighted these three regions is because electron transition in the hydrogen spectrum fall in these three regions. The highest energy transitions are the transitions from any higher energy level to the n equals 1, because they have the greatest difference in energies. Next comes the transition from any higher energy level to n equals 2, followed by the transition from higher level to n equals 3. The transitions to n equals 1 being highest in energy would fall in the ultraviolet region, followed by the lines in the n equals 2 in the visible region, and the transitions to n equals 3 in the IR region. And finally, we are back to our question. Now I know I have jabbered on a bit before answering, but I just want to make sure you're following along. Trust me, it gets easier from here, and these explanations will help you tackle similar questions with more confidence. We are left with option C and D. The lines in the visible region involve electron transition into energy levels closest to the nucleus. So energy level closest to the nucleus is n equals 1, and the lines correspond to the UV region. So C is incorrect because it's not in the visible region, it's in the UV region. Lines in the visible region corresponds to transitions to n equals 2. D, the line corresponding to the greatest emission of energy is in the ultraviolet region. That is correct. Ultraviolet region corresponds to emissions of the greatest energy. Which statement is correct about a line emission spectrum? Now note that this is an emission spectrum, not an absorption spectrum. For an emission spectrum, lines go from higher to lower energy levels so that energy is emitted. In an absorption spectrum, electrons absorb energy as they move from low to higher energy levels, and since this question is about emission spectrum, cross out the choices that absorb energy, and we look at the choices that release energy, and releasing energy when the electron moves from higher to low energy levels, so option D is correct. Which statements are correct for the emission spectrum of hydrogen atom? The lines converge at low energies. This is incorrect. We have seen before that lines converge at higher energies. Electron transitions to n equals 1 are responsible for the line in the UV region. This is correct, as we have seen that electron transitions to n equals 1 fall in the UV region. Lines are produced when electrons move from higher to low energy levels. Correct. Emission spectrum, lines are produced when they move down to low energy levels. So statements 2 and 3 are correct, and that's option C. List the following types of electromagnetic radiation in order of increasing wavelength, shortest first. Yellow light is somewhere here. We know the colors of the rainbow with GR to guide us. So we know yellow comes somewhere in between, and red and violet are in the extremes. Red is the lower energy end and violet is the higher energy end. The order of increasing wavelength is the same as the order of decreasing energy. So we start with the radiation with the highest energy. Ultraviolet first. In the visible spectrum, we have yellow coming next in this list. Red light. And then the infrared region. Distinguish between a continuous spectrum and a line spectrum. The continuous spectrum is a range of light wavelengths without any gaps. When light passes through a prism, it splits into different colors. This is known as dispersion. This is because the different colors, they bend at different angles because they travel at different speeds. In air, all the colors have the same speed, so we see light as a combination of all these colored wavelengths. A line spectrum can be of two types. It could be an emission line spectrum or an absorption line spectrum. Absorption line spectrum is created when a material, like in this case hydrogen gas, absorbs energy. Electrons are excited and they move from lower energy levels to higher energy levels. Since absorptions or emissions in the visible region corresponds to transitions from and to the n equals 2, I'll begin drawing my absorption lines from n equals 2. Since red corresponds to lines with lower energy, say the absorption from n equals 2 to n equals 3 falls in the red region. The specific wavelength of light that was absorbed from the red region would be missing in the absorption line spectrum. Suppose the next absorption is the orange, followed by yellow. The line corresponding to yellow will be missing in the absorption spectrum, followed by green, another shade of green, and blue. Now, electrons in higher energy levels are unstable and they would want to come down to the lower energy levels and become stable. When left to their own, they would prefer to come down to lower energy levels and emit the same lines they had once absorbed. That's when you get an emission line spectrum. So an emission line spectrum is a dark band with colored lines, and an absorption spectrum is a colored band with dark lines. Emission line spectrum and absorption line spectrum are complementary, as you can see that the line seen in the emission spectrum would be missing in the absorption spectrum. When you put these together, you will get the continuous spectrum. Line spectrum of elements are also called their fingerprints because each element has a unique line spectrum that can be used to identify the element. This is because the energy levels in atoms of different elements will not have the same spacings. The thinning of the ozone layer increases the amount of UVB radiation that reaches the Earth's surface. UVA has a wavelength in the range of 320 to 380 nanometers, UVB in the range 290 to 320 nanometers. Based on the information in the table above, explain why UVB are more dangerous than UVA radiations. UVB radiations having shorter wavelength will have higher frequencies and so higher energy. This makes them more dangerous and even cause skin cancer.